by a composition law that allows us to translate from one time to the next. And this is a Lie group. It's a continuous group, continuous differential group, and we can talk about the elements of the group that are near identity. And a small translation away from the identity is therefore generated by the object that is the conserved quantity, and that is energy. And that's defined by the Hamiltonian operator. And from that, we thus derived the differential equation that is sometimes known as a form of the time-dependent Schrödinger equation. Or alternatively, we can look at this as an equation for the time evolution of the state. So for example, if I have a pure state at time t0, then in a system for which we gain nor lose any information, we know that we have unitary evolution of the system, and that unitary time evolution is defined by this equation. We can then write a differential equation for the state evolving according to the Schrödinger equation. All right, and the general solution we can write down. So the solution for the time evolution operator can be written down formally in terms of the exponentiation. And if we allow ourselves for this Hamiltonian operator to be explicitly time dependent, if we have some time-dependent parameters, like a magnetic field that's changing in time, then the general form we had is actually kind of complicated. But if it is the case that this operator commutes with itself at different times, then we can write down the solution explicitly. And what we'll typically be dealing with, unless we say otherwise, is the case where the Hamiltonian is independent of time. It's some constant operator. And in which case, the time evolution operator is just the exponentiation of the Hamiltonian times the time propagation. Of particular interest, as you know, are the set of states that are the eigenstates of the Hamiltonian. And the solution to this equation, or this equation itself, is called the Schrödinger equation also. It's the time-independent Schrödinger equation. And it plays, as you know, a central role in quantum theory. In fact, you know, if you're a chemist, this is all you really care about, or a material scientist at the time. You're just solving for the energy levels. So, if we have this solution, then we can write down a simple representation of the time evolution operator in terms of the energy eigenvectors and eigenvalues, because we know a function of an operator can always be written in the basis of the eigenvectors of that operator, in which case this is a diagonal operator with these eigenvalues, right? And if we can write that down easily, then we have a nice way of writing down the time propagation, the solution to the initial value problem. So if I'm given the state at the initial time, let's say t equals 0, then we can find the state at any later time by just propagating it according to the time evolution operator. And if I insert this form of the time evolution operator here, well, then I've solved it. Because the solution at some later time is just this superposition with these now amplitudes that are given by this. So if I know what the initial decomposition of the state is in terms of the energy eigenstates, then the decomposition in a later time is just I put this phase factor on each of the probability amplitudes and resum. Okay? So, something to, of course, note about this is that the probability to be in the energy eigenstate E lambda at a later time, if the system evolves according to this, is what?
It's the same.
It's the same at any time, right? Because this is the square of this, which is this. But that doesn't mean that nothing's happening as a function of time. It would be true if there was just, if the state itself were an energy eigenstate, then there would just be one coefficient, and that would be then the same state at all times, up to an overall phase, which is irrelevant, and that's why they're called stationary states. But if the state is initially, at the initial time, a superposition of energy eigenstates with different energy eigenvalues, then the state will evolve as a function of time because the relative phases between the terms in the superposition are different at different times. And it's the relative phase between basis states that determines what the state is, right? And we saw this in an example where we looked at Larmor precession. Where we imagine we have some magnetic moment in a magnetic field. And in that case, we wrote down the Hamiltonian minus mu dot B. Take this to be a constant magnetic field. This is the magnetic moment, dipole moment. And magnetic dipole moment is proportional to, of course, a particle with a total angular momentum that is its spin is proportional to the, so mu here is proportional to the spin, and that proportionality constant we call the gyromagnetic ratio. And this is the Larmor frequency. It's called the Larmor frequency because that's what in classical dynamics of a spin in a magnetic field, that's what you get. This is the frequency by which a magnetic moment will precess in a magnetic field. This is an operator. And in that case, we could simply write this, or we could write this if you like, and I do like, h bar over 2 dot sigma. And if this is in the z direction, if B is in the z direction, and this is the Hamiltonian. And then we could just simply, if we had a situation where, say, at the initial time, the spin is, say, pointing along the x direction, then according to this, we just wrote down this. That's the time evolved state with this Hamiltonian. We plug that in. And what we found when we did all that was this is cosine the Larmor position is over 2, x minus I sine omega t over 2 spin down along x. And so the probability to be spin up along x as a function of time, what this is equal to is cosine squared, the square of this amplitude, which is 1 minus cos, or 1 plus cos omega over 2, and the probability to be spin down along x as a function of time is 1 minus or sine squared omega t over 2, which is 1 minus cos. And so, as we plot it as a function of time, what we see is an oscillation this is omega over 2 pi, omega over pi, omega over pi over 2, where this is the probability to be spin up along x as a function of time, and this is the probability to be spin down along x as a function of time. So the spin is precessing around the z-axis with frequency omega. It starts out at time t equals 0, spin up along x, and at some later time, it spin up along some other direction. At a time, this is upside down. Over 2 omega. Omega. 2 pi. Omega. Right? At a time, omega t is pi over 2, it's a equal superposition, right? When omega t is pi over 2, what is the state? If omega t is pi over 2, this is cosine pi over 4, which is 1 over square root of 2. And this is sine over pi over 4, which is 1 over root 2. So this is spin up x minus sine. It's actually equal to spin up along y. So it's precessing in that direction. And this is an example of what we call coherent evolution of the quantum state. It is coherent because we are maintaining the coherent superposition. It's not like a quantum jump that you learn about your sophomore physics, where you say it's in this energy level and then it goes to that energy level and there's a quantum jump. That's not described simply by the time-dependent Schrödinger equation, because that's not a reversible evolution. This is completely reversible. It's coherent. Later, much later, to think about things like quantum jumps, which are much more complicated to understand. All right, any questions? All right then, let's continue. So, the way that we describe the time evolution of the system by how the state evolves as a function of time is known as the Schrödinger picture. In the Schrödinger picture, what we say is that the state evolves as a function of time. Observables are constant operators. Unless there is a explicit time-dependent classical parameter. But unless part we're going to ignore for the most part, unless we want to really deal with it. Okay? Now, so there's this kind of asymmetry here. The states evolve, and the operators are constant. The observable. Now, if we think about what the quantum theory does, what we demand of the quantum theory is that we use quantum theory to predict the outcomes of measurements. That's what it's supposed to do. And at least with some probability, that's what it would. So the physical content prediction of measurement outcomes. And those measurement outcomes, for example, we have the Born rule, which, for example, we say the probability of finding a particular, say, eigenvalue of an observable is equal to say for a projective measure. Right? We could write this more generally. It could be a POVN element, and this could be a density matrix, in which case we'd have a sum over all the states in my statistical mixture. But that would be, it's generically of this form. Or we might have expectation values, which are sums of this weighted by the eigenvalues. Say the expected value of some observable function of time is equal to this. However, as you notice, the physical content that we are extracting from quantum theory isn't about the state itself, but about matrix elements. It's the matrix elements that have the physical quantities, not the states alone. Okay? So the physics depends on the matrix elements. In this case, right? Which means that if this is the thing that I want, or this is the thing that I want, I kind of have a choice of how I'm going to calculate it. Let's write this thing out explicitly. Let's say I look at the expected value of this observable and well, that's equal to, if it's a pure state, I could write this in terms of this density matrix as well. The time evolution of that dagger A right? Just plugging in for the time evolved state. So, in principle, I can think about this in a different way. I can think about that there is a unitarily transformed operator or matrix that's evolved as a function of time. This is I can define this as A of t. In which case, it's perfectly equivalent to say that, kind of cheated, I should have, that this expectation value as a function of time is equal to whatever the initial state was, but this is this expectation value.
Doesn't matter whether t is or not.
No, I'm just emphasizing this is, I'm looking at the expectation value. It's some function of time. So, in this picture, if we wanted, whatever we want to calculate, the state is constant. What's evolving is the operators. And I can do exactly the same thing for probabilities. The probability to find a certain outcome here would be equal to this. But I can equally write it as this. Where this is this. Okay. Now, to keep this notation straight, what we often do is say that there's two pictures. In this picture, we call the Schrödinger picture. In the Schrödinger picture, I say the state evolves as a function of time, and this is a constant. And this is, so in order to denote that, we'll put a little label, which often we don't do once we know what picture we're working in. But I'll denote this with that superscript S, which means the Schrödinger picture. Alternatively, in this picture, the state is constant as a function of time. All right? And so this picture is known as the Heisenberg picture. In the Heisenberg picture, we take in the Heisenberg picture, the state is constant. And it's given, it's equal to whatever the Schrödinger picture state was at time t equals 0. Okay? And we take it to the same state all times. The state is constant. In contrast, the observables evolve. So I have, and again, they are taken to agree at time t equals 0. So this operator at time t equals 0 is whatever the Schrödinger picture operator was. So that they agree at the initial time, and then they propagate forward. Okay? So we have two different ways of doing our time evolution. When do we use one and when do we use the other? That's the point. Well, we could, as we said, they're absolutely formally equivalent. They have some pluses and minuses in terms of when you might consider looking at the Schrödinger picture for time evolution versus looking at the Heisenberg picture for time evolution. So in the Schrödinger picture, one thing to notice is that given the state at all times, we can calculate all experiments, or I'm going to predict all experiments at time t. Meaning that if I have the state, the total state, then I can use this to calculate the probability of any measurement outcome, because that probability is given by the appropriate Born rule, right? Whereas in the Heisenberg picture, we must consider the observable evolving for each experiment. So if I want to know the probability of measuring outcome A about observable A, I'd have to find the evolution of this observable. If I want to find the probability of measurement of outcome B associated with observable B, I have to find that differential equation. I have to do each differential equation separately. Okay? Now, that comes at a trade-off, because this is typically easier. For a given observable. And this is typically hard. And that kind of makes sense, because in some sense this contains all the information about all observables. Whereas this only contains the information about that particular observable. Okay? So if you want the information about all possible measurements you can make out of all possible observables, well, then you want to solve the Schrödinger time-dependent Schrödinger equation. But if there's only some particular observables that you care about, then typically you would use the Heisenberg picture in terms for solving the time evolution. Okay. Of course, either picture is equivalent if you have the whole time evolution operator. If you have the propagator, if you have the whole thing, which we were able to do first in that particle, well, then you have both pictures, all, right? Because it's just related. But typically, you can't solve that easily. What else can I say about the Schrödinger picture versus the Heisenberg picture? In this, I would say the connection to classical dynamics is obscure. Meaning, if we have the state is evolving in time, it's kind of hard to connect that to what's going on. If I want to think about this, what's the equivalent classical trajectories that things would do? It's typically obscure. It's not easy to see in the Schrödinger picture. Whereas, as we'll see, in the Heisenberg picture, connection is explicit. And finally, the difference, I would say, is that if we want to consider multi-time correlations, are not apparent or easy to calculate. Whereas in this case, they're simple. What do I mean by that? Suppose I want to know what is the correlation between the spin at one time and the spin at a later time.
Well, Heisenberg, there's no time dependence.
No, in Heisenberg there's time dependence. The time dependence is in the observables.
Okay,
Right? The thing is that you could say, you know, so I could look at what I mean by a two-time correlation function and say, what is the, I have, say, two spins, and I want to know what is the correlation between the spin at time 1 and the spin at time 2. I can calculate that easily in the Heisenberg picture because they're time dependent. Whereas what would that mean in the Schrödinger picture? Because there's only one state and it has one time. So we'll come to that later. All right, so if we have the Heisenberg picture, we want to, the state is fixed, and we have to find the observable at a later time. Now, if we have the time evolution operator, then we just do this, right? But generally, we don't have the full time evolution operator. And so, as in the Schrödinger picture, we want to write a differential equation. And typically, we would solve differential equations in evolution. So what we are going to now write down are the Heisenberg equations of motion. So what is that? So what we said is that the Heisenberg picture operator, as a function of time, is given by the general is this. So this is how I get from the Schrödinger picture to the Heisenberg picture, where the Heisenberg picture operator at the initial time is the Schrödinger picture operator. Okay. All right. So let's see what is the differential equation that this thing satisfies. This is equal to take the derivative of that plus constant, sorry. That. Okay. And we know how this evolves. That is general. And that is equal to what?
Minus 5 for h bar, the Hamiltonian.
Right. Okay. And this is the adjoint, which is plus I over h bar times what?
Dagger
U dagger h. H is through mission. And when you take the dagger, you have to switch the order. Right? Yep.
So you differentiate first and then take the adjoint? Is that what that kind of means, or?
If I look at that equation, it doesn't make a difference. I can take the adjoint.
Okay.
Right? They're the same thing. So, putting that all together, what do we see? Now, h and u commute, right? Because u is a function of h. So I can put it on the other side, no problem. So this is equal to I over h bar, h, u dagger t, a Schrödinger, u t minus I over h bar, h, u dagger, a in the Schrödinger picture, u, t. Right? And this is A in the Heisenberg picture. And so is this.
Zero?
What did I do wrong? I did something wrong. Oh. This is on this side.
H doesn't necessarily.
Commute with A. If it did, that would be 0. Absolutely. But it doesn't necessarily.
So it's commutator.
It's the commutator, indeed. So what we find is that the Heisenberg equation of motion says that the time derivative of some observable in the Heisenberg picture is given by I over h bar plus I over h bar, the Hamiltonian commuting with this. Now, I want to make one small point, which is a subtle, very subtle point. If you come back over here, written in very small type here, is something that looks like that equation, but it's not that equation. It's not in one important way. It's got this minus sign. This is a Schrödinger picture evolution. Because even though it's the operator, it's the state. The state is evolving. Okay? Because in this, when I have a general mixed state, the state is an operator. Okay? That's the Schrödinger equation. That's not the Heisenberg picture. This is the Heisenberg picture. And in this case, rho is constant. So in the Heisenberg picture, the state is constant. In the Schrödinger picture, the state evolves. The operators are constant. In the Heisenberg picture, the operators evolve and the state is constant. The psi is constant. All right? Now, one should note that this looks, in classical mechanics, we're going to talk about this in more detail in the coming lectures. Let's say I have a Hamiltonian h, which is a function of position momentum. Okay? And suppose I have some observable physical quantity. Which is itself some function of position momentum. It might be position, it might be momentum, it might be angular momentum. Okay, it's some observable, right? And I want to know, how does this evolve as a function of time? Do you know how to get that if I have the Hamiltonian? Have you done that in classical mechanics? There's something called Hamilton's equations of motion, right? So Hamilton's equations of motion, that's why it's called Hamiltonian. Have a general form. And that form could be written explicitly as this. Where this is known as the Poisson bracket. And it's equal to the partial of the first thing with respect to x times the partial of the second thing with respect to p, and the other way around. Okay. Those are the Hamilton's equations of motion in a very generic form that you may not have seen if you didn't get to this point in classical mechanics. These are Hamilton's equations of motion. Now, there is something that looks pretty darn similar between the classical Hamilton's equations and the quantum Heisenberg equations. We will see in the way in which, in some sense, this is some appropriate limit of this. But we see this parallel. And Dirac noticed this first and said, oh yeah, we quantize, there's some way in which the Poisson bracket becomes the commutator. But this looks very similar to the classical dynamics. Right. Okay. By the way, if you don't believe this is true, let's just do a quick example. Suppose I have a free particle. What's the Hamiltonian?
P squared over 2m.
Thank you. So, let's say A of x and p is position. And I want to know, how does the position change the function of time? Well, oh, maybe I got it backwards, didn't I? Yeah. Yeah, that's right. So now it makes sense. Rate of change of this with respect to time, well, the partial of h with respect to p is p over m, and the partial of a with respect to x is 1. That's the velocity. Right? And the rate of change of momentum with respect to time is 0, because momentum is conserved. So that's a very simple case. Generally, this would be the hx, which is the gradient of potential, and there's no potential, so it's 0. All right, very good. Now, integrating the Heisenberg equations of motion is done typically in a case-by-case basis. But we can write down a formal solution to this, which is informative and sometimes calculationally useful. So let's formally integrate this. So if I just look at the integral of that, that says that the Heisenberg operator at time t is given by, well, there's an initial condition, and then plus I over h bar, the integral from 0 to t of that. That's just writing down the integral. I didn't really solve anything here because I have the time-dependent operator on this side of the equation and on that, so not really a solution yet, but I can iterate now. Now I can plug in this solution again, and I get, so I'm going to get a formal series here. So now I plug in okay, so what I did here is I integrated once, wrote down the formal solution, and now I plugged in for this of t prime. And this at t prime is equal to this times the integral from 0 to t prime times the integral over t double prime. Yeah.
Why isn't it integral from 0 to t for both of the integrals?
Because I'm plugging in here t double prime, right? So let me see. So when I plugged in here, I said this at time t prime, I plugged in for that, is equal to this at time 0 plus the integral to t prime, because that's the variable, and then integrate t double prime. Minus I over h bar, h, the Heisenberg picture operator, t double prime. So I just plug that in. I mean, this is just changing this to t prime. Is that clear now?
Yeah.
So this is what's called a Dyson series. Yeah.
So just real quick, is that on the second term, is that first dt, is that a dt prime, or is that just a?
Yes, that's a dt prime. Thank you, Steve. Indeed. Yeah. Now this would be a way of getting a power series solution for short t, but we can look at it as a general power series solution. Let's so if I look at this, this thing is actually independent of t, right? So this is equal to t times that commutator. And I'll just write it out. Right? That's what that equals. Because this is independent of time. Okay? And then I have this term. Well, this I can't do anything, but I can plug this one in again. It'll be an A0 A at time t equals 0, which is the initial of A, the Schrödinger picture A, plus a commutator of a commutator with a commutator, right? So this guy, when you do that out, is going to be equal to 1/2 t squared if you do that integral, because you get t, and then the integral from 0 to t is 1/2 t squared times the commutator of h and A plus order t cubed terms. So what we have thus is a way of expressing the solution as a Dyson power series. Which says that in the Heisenberg picture, the solution at time t, which is equal to this, is given by the sum over powers, 1 over n factorial minus I over, or plus I over h bar to the power n the commutator of A with h 0 n times, where this is a shorthand for h commuting with h commuting with n times. Okay, and this is often a useful thing to use. Or I wouldn't say often, I'd say once in a while. This is really a result from weak group theory. Let me explain what I mean. Suppose I look at the following conjugation. So remember, if we thought about these, say, B as a anti-Hermitian operator, this is like a generator, this is like a group element. So this is like a U and a U dagger, right? So if I have this kind of thing, and I do this, I write each one of these as power series, I multiply them together, and I do all the commutators, I get the following result. This is equal to the sum over n, 1 over n factorial, the commutator of B with A. I forgot time here, didn't I? Right? So if we have U dagger of T, sum A UT, and this is equal to e to the plus I H T over H bar, A U to the minus I H U over H bar. Well, this result is this, where now B is equal to I times the Hamiltonian times time over h bar. And you plug that in, and you get that. Right. Okay. I should say there's a related result that I want to just note here. Suppose I have two Lie group elements, e to the A and e to the B, and I want to combine them together. Okay? There's a composition law. Now, this generally does not equal this. If A and B don't commute. If they do commute, then you could do that. But if they don't commute, you can't do that. However, what is true is that e to the A times e to the B equals e to the A plus e to the B plus is there a half there?
One half of time.
Yeah, it's a half. Half times the commutator of A and B plus higher order terms. Okay? And if the commutator, we'll use this a lot when we talk about the harmonic oscillator. If the commutator of this with either A or B is 0, so if this thing is some operator that commutes with both of these guys, well then you can factor it out. And then what we have is that e to the A plus B is equal to e to the A times e to the B times e to the minus a half the commutator of A and B, if this is true. This is a form of what's known as Baker-Campbell-Hausdorff. So pH So these are some results we will need. All right, let's do an example. That's the same example, but now in the Heisenberg picture. Let's look at law of perception. Oh, look how convenient. Is this awesome Blackboard form or what? Okay, so that's what we're going to do. We're going to look at this problem, but we're going to look at it now in the Schrödinger picture. I mean, in the Heisenberg picture. So we want to find the Heisenberg equations of motion for the operators. So this is equal to, so this is my Hamiltonian. So my Hamiltonian is this, or I could write it equivalently minus omega s. Right? So I want to find what, and this is something to keep in mind. When we write it this way, this is the Hamiltonian. And this Hamiltonian is an always constant in time because the Hamiltonian commutes with itself. So it doesn't evolve. And so I can think about this as the Hamiltonian in the Schrödinger picture or in the Heisenberg picture. It's the same. Right? So now I want to find the equations of motion. Let's just, again, just to emphasize this. This operator, everything in the Heisenberg picture, so we're not going to write little h's everywhere. We're in the Heisenberg picture, is equal to I over h bar, the commutator of the Hamiltonian with SV. And what is that? Plug it in. 0. This is SZ. SZ commutes with itself, right? And that's as we expect. So SZ as a function of time is SZ at 0, which is the Schrödinger picture SZ. This is h bar over 2, 1 minus 1, 0 in the basis. Let's see, right? It's constant. And that's, as we expect, the z component of the spin is a constant of the motion because it commutes with the Hamiltonian. Okay. What about the other components? Well, let's look at the x component of the spin. According to the Heisenberg equation of motion, this is equal to that, right? Plug it in. Minus I times the long arc frequency over h bar, the commutator sz with sx. Right? Which is what? So there's it's an I times sy, is it plus or minus? How do we know? Because it's a cyclic permutation, right? So this is I times sy. Right? So this is equal to, or h bar. Right? Right. Didn't take away my h bars. That's what it is. So this is equal to omega sy. Right? And similarly, sx, which would be the other side, because this is minus I h bar sx. So those are the Heisenberg equations of motion. And we can solve these simply by now, if I take a second derivative, well, that's omega times the first derivative of that, which is minus omega squared sx. And similarly, the second derivative of sy is minus omega, the first derivative times sx, which is minus omega squared sy. So both of these x and y satisfy this differential equation. You recognize the differential equation? I hope you do. That's a simple harmonic oscillator, ODE, right? And we know the solution. The solution is that solution to this equation is, well, there's an initial condition we need for both the first, what it was at time 2, 0 and its derivative. Right? That's the general solution at time equals 0. And similarly for y. Okay. So, what this says then is that the x component at time t is equal to the x component at time 0, which we just call Sx. And then the first derivative at time t equals 0 is equal to omega times this at time t equals 0. But that's just sy. So this is plus sy. And sy at time t is equal to sy cos t minus this minus sign s. We have solved the Heisenberg equations of motion there. Now here's something that is often confusing. These are the Sx and Sy operators as a function of time. They're not constant operators. So what are they? What are those operators? We can write a matrix representation of those. So Sx as a function of time. So in the basis, let's say the standard basis of spin up and spin down along the z-axis. What are these operators? Well, let's write down the matrix representation. What does Sx look like in this basis? Well, it's h bar over 2 times sigma x. And what does sigma x look like? Well, it looks like that, right? That's the Sx operator. So when Sx with no time dependence is the initial one, which is the Schrödinger picture one, which is the one you know. Okay, that's what it is. Times cosine. And then we have Sy, which looks like that. Okay, so that's equal to h bar over 2 e to the minus I e to the. In this basis, this is what it looks like. It's not a constant matrix. Okay. In fact, when omega t is equal to pi over 2, what does this matrix look like? If this, what is Sx at t equals pi over 2?
Pure state is.
We just got to plug in here. Omega t is pi over 2.
0 or 1.
E to the minus I pi over 2. These people.
Negative I.
Negative I, right? And then here it's plus I. So what does this matrix look like?
That's why.
This one is sigma y. So sigma x at this later time became what? Sigma or sigma y. This is what's confusing about the Heisenberg picture. The matrix is not constant with a function of time. But you have to just, and that's exactly what you see, right? When omega t is pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is 1. Sigma x at time t becomes sigma 1. And vice versa. All right, so with that said, at the end of the day, this is used to calculate things. For example, if I wanted to know what is the mean value of the spin along, say, the x, y, and z directions as a function of time, what is it? Well, this is what it is at time equals 0. That's constant, because that's irrelevant. And this is equal to whatever the initial value was. That's exactly what we saw in the Schrödinger picture, though it wasn't as obvious what the mean values were, because we calculated the probability amplitudes. And then we'd have to translate those probability amplitudes into expectation values. In the Heisenberg picture, it's just obvious what's going on. The mean value of the spin is precessing. It's precessing around the z-axis with the Larmor precession frequency. So it's exactly the picture we did before. So this is the spin along the z direction. I'm sorry, that's the magnetic field along the z direction. And we had some initial magnetic moment. It Larmor precesses with frequency omega around the z-axis. Its component along the z-axis is constant, and its component in the xy plane is precessing. That's the mean value is doing that. So in some sense, it looks exactly like a classical problem. If you solve this classically for a magnetic moment, it would do exactly the same thing. The mean value in this case follows exactly the classical trajectory. Now that's not always true. That's a very special thing about this kind of Hamiltonian, which is the linear. We will see the distinction, but in this case here, the mean value of the magnetic moment as a function of time exactly follows the classical trajectory. And we can just see that. Okay. We will see the distinctions under what kinds of Hamiltonians does the thing follow exactly classically, and when does it deviate? When do the mean values deviate from classical motion? Even though the mean value is following the classical trajectory, doesn't mean that this thing is classical, right? Because if I think about this as a spin, if I measure it, it's not like I'm going to find that value. If I measure along the z-axis, I'll find it this way or that way. What's really precessing here is the probability amplitudes, or the predictions of what outcomes I will see. Although we often think about it as, if you're an NMR guy working somewhere, you think about, oh, this spin is precessing. Well, it's not quite right. It's not a classical vector that's doing that. It's really telling you about what the probability of the outcomes is, how it's changing. All right, very good. So, Study hard for your exams.